Right, yeah.
And the recording is on. We can start.
May I sit on the window?
Yeah, yeah. And if it's too cold, then you can just close. Yeah. Okay. Yeah. So topic is just some algorithmic techniques. So last lecture, the goal was to prove some techniques to prove that the problem is fixed parameter tractable. So do you know what is fixed parameter tractable?
No.
Okay, then let's repeat. It's good for everyone to repeat. So, so first we have parameterized problem, and so what is the input? So the input consists of two things, just like for example a graph, and in the click problem we have a graph and an integer, and the question is can we find so integer k, can we find k nodes in the graph that are pairwise connected? So in parameterized complexity, one part of the input is called parameter, and we want to find an efficient algorithm assuming the parameter is not too big. That's the whole idea. And so the bound on the runtime that we aim for is, so if the parameter is an integer, it is any function, any computable function of k times and then input size to the power of 1. Hello. Oh, you're nice to see you. Quite impressive for completely optional lecture that there are so many students. Okay, so so a problem is fixed parameter tractable, and so that is considered a click problem. The input is a graph, then the parameter is k, and the question, do there exist k nodes that are pairwise connected, the click of size k. So it's fixed parameter tractable if there is a function that runs in time some function of k times a polynomial in the input size. So an input size will be this will be like n squared if there are n nodes. So then a graph, we fix some representation by incidence matrix, and the parameter in unary. So that's how we define the input size. And we discussed that we could drop this from the definition and it's still the same.
Yeah.
So it's still the same problems are fixed parameter tractable. And
It's
so
important to notice that the parameter doesn't depend on the input. These parts are independent.
Yeah. And this
Because if k is a function of n, then it's kind of doesn't make sense.
So
if k is a function of n, then the definition doesn't kind of
k is part of the input. And here I gave a bad example because today we will learn that click problem is very unlikely to have such an algorithm. However, there is the vertex cover problem. Nodes that cover such that each edge has an endpoint in one of these k nodes, and there we proved that the problem is fixed parameter tractable. And so the programming exercise is to implement this algorithm and make some clever choices so that you get, I don't remember how many, like 60 examples there are, and if you program it clever you should have 50 right within 2 seconds.
And we just submit the IPAM file.
Yeah. So
this exact file that you send us. We don't need to convert it to .py.
Yeah. So the task is some Python notebook. Sorry, I cannot program well, so I use Python. My plan was to learn C++, but each time I want to do it, there is some urgent task that has to be done fast, completely unexpectedly. And then I'm tired, and then it's time to read the next lecture, and then there is some meeting. Okay, but one day I will do it properly and learn C++ and give you a nice grade there. But
I have a question.
Yeah.
I'm not sure that it's a very clever question, but you said that which a click problem doesn't probably doesn't have a good algorithm. So can we use a reduction from click problem to vertex cover problem, for example, and use the algorithm that is for vertex cover?
okay, it's very nice question. So this is in the third point. I will discuss it, but I can already tell it. So okay, what happens with the parameter? So if we have a vertex cover and
it inverses,
yeah,
we get
it will become
k.
n minus k, and so if k is small, it's suddenly
I see. Thank you.
Okay. So this is the general idea, and then in the last two lectures there were many techniques to prove that a problem is FPT. For example, knapsack problem is a very famous one. If we use the target sum, like the total value, and as parameter, then we can use dynamic programming, and the runtime will be of this form. So do you remember? Because the size of the table will be, so it cannot be solved in polynomial time, the knapsack problem, because our inputs are given in binary. And so the values can be huge, and that means the table is of exponential size. But if the parameter is the value, then the size of the table is if parameter is number of objects, no, that's stupid. Sorry, if the parameter is the value we aim for, some v, then and if all values and sizes are integers, then the table has size v times number of objects. Right? And so if the parameter is v, then it becomes fixed parameter tractable. So even if the input size is huge, even the value of v is huge, we just have easy dependence on the parameter. So yeah. Okay, this is kind of a silly example. But we had a nicer example using set cover problem last lecture, where we used the size of the universe. So you get a list of subsets of some universe, and the subsets can be huge in size, given the size of the universe. But if we use dynamic programming, then here we have 2 to the power size of universe times number of subsets. Because our size was our table was size of universe to the power 2 to the power size of, so all subsets of universe, and then we iterated over all the subsets. So the size of the input is proportional to the number of subsets in this. Okay, that's a bit difficult. Let's not try to repeat things and just start with what we plan to discuss now. So first point, we'll consider the vertex cover problem. So let us remind what is a vertex cover. So it's just, here is a graph, and an input of the vertex cover problem might be something like this. So a graph and an integer. So parameter k is part, so here is the graph, here is the parameter k, and we want to find 2 nodes such that all edges have at least one endpoint in the selected node. For example, we might select these two nodes.
And it doesn't work.
And that doesn't work, yeah. And so this is, here the answer to the question is no. There do not exist two nodes such that every edge has an endpoint in these two nodes. However, if we are allowed to use three nodes, so this instance of the problem does have a positive answer. Yeah. So the naive algorithm, again, just because people might have forgotten, I know that people who were last lecture here already know this. So there is a trivial algorithm that solves this problem in n to the power k, n number of nodes, k the size we set for. We just brute force over all subsets of k nodes. And if one of them covers all the edges, then we know the answer. But this is not the runtime we want for. We want f of k times n to the power of 1. That's the runtime we want. N to the power k not allowed for FPT. So brute force doesn't work, we need to do something more clever. And unfortunately, or maybe why not, let's repeat it. Yeah.
So we invented the branching algorithm and some reduction.
Better branching algorithm.
Yeah. So what's the minimal thing we need to know to understand that we can do it in this time?
What's
the
the
branching? Simple branching algorithm. No?
Yes, simple branching works.
Yeah.
Yeah. So you learned about branching in other courses or not?
No, we had
Not
a
at all?
task about branching algorithm.
Yeah, we had to.
From another course?
No, from this
you.
course.
Only my...
Yes.
Oh, this is very important.
we didn't do much on graph algorithms and software engineering at least.
And Hamiltonian path problem, you don't know how to solve
I
it?
have read this in Sipser's book.
No, but if you really want to solve this, and there are a bunch of techniques, and I was in some exams at some point, I had to listen to explanations, and it looked like, but it was some years ago. Yeah. Okay. So it's you spend a lot of time learning useful stuff, which is a good thing. But there should also be interesting stuff in the learning plan. Okay. Yeah. So the branching out.
The task on branching is homework for this.
Yeah.
module.
Yeah.
As in
And that's like the grade is 4 things. Homework, colloquium, exam, and the programming exercise and the deadline 31st of March.
That's okay.
Yeah. But by the way, on the 28th of March, I will be traveling. I will take my laptop with me.
So the deadline is actually 28th.
No. I will install it at home, and then unless something stupid happened to the internet, I mean it blocks. So but I expect I will open the laptop, everything will work.
Oh, okay.
Is it here?
No, it's not this one. No,
Why
if
you asked?
Start to steal things, but it's the same software.
Is it streaming now?
No, I didn't
No,
stream.
it's recorded.
Yeah, it's only there. Sorry, I forgot to stream.
No, I don't think it like.
Yeah, now it's
who did-
already too late. Yeah, people will
And,
have
and
plans.
everybody that wanted to come is here.
Yeah, but maybe someone wanted to attend online. Oh, and they're complaining on Telegram maybe. Oh, no messages on Telegram. Okay, we're good. Yeah. Okay, I was saying that let's do the branching algorithm. So somebody. Okay, that's too easy. Let's just say how it is. So we look at one node.
How do we actually select the node to branch on? We always select the node with maximum. Okay.
No, don't worry. Okay.
It becomes kind of greedy algorithm actually if we do it
Well,
the obvious way.
Yeah.
heuristics.
Yeah.
It's called heuristics actually.
So I think with greedy algorithm, you can have half of the mark just with greedy algorithm.
As far as I
Right.
remember, at the presentation there was an algorithm not with vertex, but we take any edge.
Yeah. and
But
then
with the vertex, it's more naive.
yeah,
and
but
we-
taking any edge degrader, you will pass very few. It's too slow.
Okay.
It will only
We
2
need to-
out of 10 or something.
We need to think of selecting the nodes
Yeah.
correctly to branch on.
Yeah, but you already said.
Okay.
It's okay.
But
Don't
it's
worry.
okay.
Yeah.
No, like it was the first thing I thought of. Like I thought,
Yeah.
okay, I'm doing this.
Okay, so let's quickly say what is this. So we pick a node and then we start to think. So either this node is in the vertex cover, and then we can remove this node and of course the edges disappear. And then we reduce, so the branching algorithm will create 2 new instances. So either we believe this node is in the vertex cover, and then for remaining edges, we search for a graph that cover this thing. So they are removed, but now we only have 2 things left and the 1 branch. And then we continue searching. We take another node, remove it, and look what is left, but now we can only use 1 node, and eventually if the answer propagates yes here, then we say yes here.
And at this point we can invent a clever technique when we have the parameter value 2 and we
Yeah.
have the graph, and we can start traversing all the structures of size 2, like the triplets of nodes.
You're
and all that
confusing with the degree. If the degree of the graph is at most 2, then you can output the answer.
stuff. Yeah, sure, yeah, I got you.
This is what we discussed.
Well, actually, this example still.
Yeah.
is
Okay,
used.
now let's speak about the second branch. So if we decide that this node is not in the vertex cover,
Then all the other neighbors
yeah,
are in
all the neighbors need to be in the vertex cover, otherwise the corresponding edges are not covered. And so we have, okay, but I'm explaining it for you. So if you don't pay attention, I will directly switch to the
No, I know this problem.
okay, you know how to branch it.
No, I don't know
Yeah.
the solution, but I'm listening.
Yeah. So we will delete these 3 nodes and then decrease the parameter by 3. But if I delete these 3 nodes, nothing is left.
No, it's just 2 isolated nodes.
No. Oh yeah.
2 isolated.
Yeah,
nodes.
no edges are left.
Yeah,
Yeah,
no
so
edges.
that's in the base. We check if there are edges, and so okay, just an isolated nodes. And here we have 3 minus 3, and so it's here. We get yes, and then we aggregate after the recursion. We get yes, and so now the theoretical runtime. So how much is it for this algorithm? If you
Complexity.
Yeah, complexity. So we need a formula of this form, and maybe to verify it's of this form, you can say what is the runtime.
The runtime is empty.
Yeah. So we of course we continue. If k is larger, here we get k. In general, we have here k. Here we have k minus 1, and here we have k minus number of neighbors of the chosen node. Okay, of chosen node, and then we continue. So we pick again a node, and then split into 2 branches. So each time in the recursive call, we know that the number decreases by at least 1. So
So
the
it's 2 to the power of k poly n.
yeah. So the size of the recursion tree is 2 to the power k, and to construct each node, we use n to the power of 1 time.
Oh, but we need to copy in a graph each time. It's n square, no?
Yeah, n squared. But yeah, you
No,
can
it's
have n
squared.
squared,
Ah.
and then if you use
Yeah.
Vertram model, you can basically if you
If you use
Masker and Vertram model, it will be linear and okay. These details don't matter. We need poly n, and that's enough for FPT definition.
if you use NumPy, for instance, you only create views on the matrix, adjacency matrix, so it's literally like O of n. often just to sum the degrees, and you don't need to copy anything.
Как называется?
Ну, NumPy просто, типа в NumPy ты когда получаешь по индексам доступ к этому массиву, у тебя просто вьюха
I thought
создается, и
that
всё. Там ничего не копируется.
it was supposed to use this algorithm in the second part of the home task, and I thought that it's not allowed to use this in the first part of the home task.
Oh, sorry. Yeah, no, you can use the same function for both parts. Yeah, you were worried about it,
Yeah,
but
yeah.
then I said no, it's. And then there are two scores in the bottom of the reply email, and the
Okay.
result is just the average of the two. So.
Can we choose edge instead of nodes? Will it work? Like we.
Yeah, it also works.
Okay.
So you can look at an edge and then say either this node will be in the vertex cover, and you check, otherwise you say let's not put this node here, but then the other one must be in the vertex cover, and like again you get a binary tree, but this will work faster.
Yeah,
It
I
is-
have time
Yeah.
exception.
Because we use your technique.
It is
It's like the
asymptotically
node.
equivalent. Actually, it's still 2 to the power of k poly n, but this
Yeah.
obviously works slower
Okay.
in practice.
Yeah.
Like statistically slower. I don't know how to say it, but kind of seems
Yeah.
like this.
So, and now we will apply a technique. Our plan is, when we get an instance of vertex cover, to get rid of all nodes except 2k nodes. And then our graph can be in the millions, and maybe k is 200, but then suddenly we get rid of 1 million nodes and end up with 2k, like 400 nodes, and this is much more efficient. Okay, and so how it works is we will first create linear programming problem, and we will check whether there exists linear programming solution. And if this linear programming solution does not exist, then we know answer vertex cover does not exist. So we will relax the vertex cover problem. And roughly said, the relaxation is that we allow a node to be a fractional part of the vertex cover. So we will assign numbers to all the nodes. Like we will check whether it's possible to assign numbers to the nodes, like this, such that for every edge, the sum of the two endpoints is at least 1. So that's what. So for every node, a normal vertex cover problem, we decide for every node, is it in or outside the vertex cover?
So it's 1 or 0.
Yeah, 0 or 1. But now we allow relaxation. We can say it's a little bit in the vertex cover. For example, and here is a solution. So for every edge, we see that sum of endpoints in the triangle is at least 1. Sorry, it's not a solution, because here for this edge we have a problem. We have 0.5 and 0.1 here.
I didn't understand how do you do that relaxation, or how
Yeah.
do you assign these values?
Yeah, okay, so I let us LPVC problem. What is this problem? So input is the same, graph and the number k. The question, does there exist x1 till, okay, so does there exist a mapping x from vertices to non-negative real numbers, such that for every edge so an edge is a 2-element set of nodes. So for every edge in the graph uv, we have x of u plus x of v is at least 1. So is it clear, the question?
So we need to find the values.
Yeah. And sorry, so the input is a graph and a number k, and the aim is to find the sum of all x's to be smaller than k, integer k, such that we have like a fractional vertex cover and sum of all x v, so over is at most k. Okay, I'm a bit lazy. Here we sum over all the nodes in the graph. For example, if the input is this thing here, 2.5, then the answer is yes.
It's not the integer, then it's float.
Yeah, sorry, yeah. Okay, let's say we have two copies of this graph. So do disjoint. By the way, so graphs do not need to be connected, also in the programming lecture. And also after you remove a node, graphs can become disconnected, so you need to deal with this. I mean, that's not, you can ignore this, but you need to think about it when you're debugging. And here, the answer is 5 is a yes instance.
Why can't we just allow partial?
Yeah, we can allow this.
Floating point k.
Yeah, you can allow this. It just.
It still means like kind of the size of the vertex cover, but if it's floating point, it kind of means the.
Yeah. Okay, rational.
Okay,
rational.
I guess. Okay.
You're right. It doesn't make sense to require. But okay, here it's nice that the integer problem has no solution. So in original vertex cover problem, the answer is no. Because we need at least 3 for each component of the graph. But now the answer is yes, because we give 0.5 to all the nodes. And here the same.
And why is it a reduction? It's not a reduction.
No, I just defined the problem, the variant of this problem.
So it's just another problem.
Yeah, another problem.
Yep.
And I know that if here the answer is no, then for the same input the answer here will be no.
Okay.
Again?
So if for LPVC, linear programming vertex cover, the answer is no, then here the answer is also no for original.
Okay.
But here is an example where answer of original is no, but here answer is yes. So it's a relaxation of the problem.
Can you please define or explain what is linear programming very quickly? Like
Yeah.
Abstract.
It's very important.
What is
problem.
linear programming at all?
So here the input will be so two matrices and m times n, and b is a vector. I will need to check the dimensions later. And the question, so exist x. Oh, but we don't need. Actually, it doesn't matter because you can always. Does there exist x such that a times x is smaller than b?
Okay.
And so I think in typical variants they want x to be non-negative. So
Yeah, because
does there exist?
X.
But it doesn't matter because you can add extra. So here you get a bunch of inequalities on x. So this is a matrix, and hopefully, I did it right. So here are matrices, but inequalities
It's just
between is just a system of
linear
inequalities.
equations.
Yeah.
Inequalities.
Yeah. So that's the question. And here linear programming is a special case. So this is a special case of this problem. So this can be solved in polynomial time, but you need to be careful because algorithm doesn't work very well. So NumPy has algorithms for linear programming, but usually if there are less than 100 variables, my experience is it's okay. So you get an answer within a second. But if it's huge, you can have bad luck and the algorithm is unstable. But usually it tells you like, I'm unstable, my answer can be wrong.
Okay.
Yeah, so it's still, and
Is there a general way to solve the problem?
Yeah. Well, normally you should have a course and learn these algorithms. It's the typical worry for many students.
Something with pseudo inverse matrices.
No. It's inequality here. So interior point methods, like in Clauser's interior point method, they teach. But there are actually 3 algorithms, but I never learned it myself.
Okay. Thank you.
Yeah.
Thanks a lot.
I will fix this as soon as I have some time. Okay.
Петь, давай откроем окно. Или хочешь сядь на мое место, если холодно?
Не, пока что еще.
Мне кажется, что я просто более хладоустойчивый. И мы сможем сидеть с открытым окном дольше.
Yeah, I didn't study.
Меняемся.
Ну или типа.
Если тебе жарко.
I didn't study informatics, so I changed. I studied physics and engineering, so I didn't learn what I know. And then for research, I decided I want to do something useful in life because I found this physics theory, high energy. I found it complete. I learned string theory, and then I didn't want to learn it anymore.
Wow.
Yeah.
Well, but it's actually a higher class education.
Yeah. So
It is a completely another level of the high energy theory, the string theory. The theoretical.
It's a lot of mathematics. But then, if you learn one thing, like mathematics, it's kind of transfers between fields. With a lot of mathematics, if you learn one field, you can faster learn other field. But then I should learn the other fields, of course. But then for research, it's like you need to write a lot of papers. And then it's not so much time to learn extra things. So, okay, I'm a bit distracted.
Okay, so we are in LPVC.
Yeah.
context
There are
right
good
now.
algorithms for this, but I will explain you a special algorithm that works for this thing. And so you can apply, solve this for quite huge graphs. But first, let us understand why this problem is a special case of this problem. And yeah,
If the vertices are given by adjacency matrix, and we find x, then x is just a linear operator, right?
yeah. So let us say carefully what are these inequalities. So know that this is just a set of inequalities. So let us write down. Let us take again our same graph, but now just one copy. And so let us number the nodes. So here we will have x1, x2, x3, x4, and x5. And let us write down all the inequalities that we need. So here we need that sum of x's is at most k. Okay, so let us have a false guy. So here we will have x1 plus x5 is at most 2. And then for every edge, we need that, so there is an edge x1, x2, we need that the sum is at least 1. And then the same x1 plus x3, so for this edge is at least 1. And so we do it for all 6 edges, no, 6 edges, x4 plus x5, and that's it, it's bigger than 1. So note that here we have bigger than, so it's not of this form. But we can do it by flipping the signs. So we say -1 is smaller than 1. Smaller than -1. And so on. Okay,
And the b's,
that's it.
And the b's are just k.
Yeah,
So
B is the vector here.
Uh-huh.
So 2 and then followed by all -1s. And then the a's we get, A will be the vector. So on the first row we have all these 1s.
It's adjacency matrix with,
Yeah.
with an extra row.
Not,
No, why not?
it's incidence matrix.
Or incidence matrix, yeah.
Yeah. And then below the 1 comes, and all with minus, yeah. Okay, so now we understand.
It's minus incidence matrix. Can we please write it down?
Okay, and
No.
I work it out. So for the first we have minus.
No, I'm not talking about working. Okay,
Yeah.
so it's actually minus incidence matrix with extra row times x is equal to.
Yeah, almost. So the minus is only on the inside.
To be
precise, yeah. To be
why,
precise.
why can't we just switch the signs here and here?
Because then we have bigger than. We cannot do this. Yeah.
Okay. Minus incidence matrix times x
This
is less or equal to b, where b is what? It's
just
k.
2 minus 1 minus 1.
And how do we get these values?
They're just all their.
No, what is this value?
Yeah.
It's ones. Okay, so it's k 1 1 1 1.
Minus 1 minus 1. Yeah.
Okay, thanks a lot.
Yeah.
Now it's much better.
Now you believe it's special case, everything is clear.
Yes.
Okay. Yes. Okay. And so we give this to the solver or the special algorithm we will discuss later. And so we get some fractional x. Now the question is, if we know these fractional x's, how does this help us to throw away some nodes? And it works as follows. So we will consider 3 sets of nodes. The nodes where the value of x is exactly 1/2. This nodes where it's smaller than 1/2 and where it's strictly bigger than 1/2. And the plan is that all the nodes where it's strictly bigger than 1/2 we add to the vertex cover. The nodes where it's strictly smaller than 1/2 we remove from vertex cover. So we get rid of both sets and we continue with this set.
And why do we do this? We do this because we want
And then we have an equivalent instance of
having
vertex
a
cover.
solution for LPVC. We want to construct a strict solution
Yeah,
for
yeah.
vertex cover.
And so we will remove nodes until the only solution for this problem is a solution with all 1/2s.
Mhm.
Again, we will remove nodes from LPVC until
Yeah,
the
so we do it
solution-
iteratively. So we throw away these and these nodes. When we add these nodes, we decrease k. We decrease this node and we keep throwing nodes away until our solution is 1/2 for all the nodes.
Mhm.
What do we do with k when we throw away the nodes that are less than 1/2? Okay. So we're given
We
an
keep the
instance of
same k. So if
okay.
if the value is less than 1/2, we understand that this node will.
doesn't participate in
Yeah.
vertex cover. So we're given an instance of an LPVC problem, then we give it to solver, then we have all the weights of the vertices, then we throw away the last two, then decrease k by the size of
Yeah.
this that are bigger than 1/2.
So
And then we
Yeah.
repeat it with the nodes that have weight 1/2 exactly 1/2 until that.
Yeah,
Until
so
we all
first
have
I realize I didn't tell you something correct. So in LPVC, k is not part of the input. We want to optimize k. Actually, I should. Sorry, I was lying to you. So, so okay, what you can do is solve this problem. If the answer is no, we know that for this the answer is no. It's one thing. But in linear programming, you get A and B. You actually get A, B, and some C. And here it's important that it's and the question is optimize. Optimize x C transpose, sorry, C is of length n, and you need to optimize this product such that such that this condition is satisfied. I will write it again. Optimize C transposed X for X non-negative such that A of X is smaller than B. Sorry for my mistake. So that's the real problem.
C transpose X. And so what is C what is B in our case, like in this?
B is the
What
same
is-
as before.
But it contained K.
Before it contained K. Yeah. Now C will be just the all ones vector, and A will be the incidence matrix. B will be all minus ones. Sorry, A is minus incidence matrix, and B is all minus ones.
And what is C?
C the all ones vector.
And where is K? What do we optimize? We just find the smallest X.
Yeah. We want to find so linear programming LPVC is so the question lets me write it again. So the question minimize x1 plus x2 and so on plus xn such that for every edge this inequality is satisfied. I'm sorry, this optimization problem. But then we have the same conclusion. If this optimal value is smaller than k, we can directly know for our original problem the answer is negative. And for exactly the same reason, this is a special case of this.
Can you write it again? Minus incidence times.
Yeah.
So A is minus.
A is minus incidence matrix. B is equal to the all minus one vector, and C is equal to all ones vector.
Wait, why did we drop the first line of A with ones?
Yeah, because I took a decision problem, and so I wanted to decide whether we could have this at least k, at most k. So, and optimize means minimize. Okay.
Okay, so the solver returns us C transposed X.
Yeah,
So
this
it's
value
just the
and
sum.
x.
Just the sum
Yeah,
of
it
elements
tells,
of X.
yeah, the solver tells us two things. So the
Mhm.
target value and well, basically x, because we can compute C times C transpose
okay,
x.
yeah,
Yeah.
So it, and we compare the sum of X to K
Yeah.
that we want to find.
Yeah.
We want to find LPDC of size less than weight less than K, and we compare the sum of X to it, and if it is bigger, then we can leave null.
Yeah, exactly.
And if it's smaller, then what we do, we apply this to.
Yeah, if it's smaller, we apply this rule. So we throw away all nodes with x is bigger than 1/2, and decrease k for each node that by the number of nodes that we throw away for this reason. And then we just simply delete these nodes because they will not be in the vertex cover. And then we run it again on these nodes. And then we check whether again we can throw away, and we keep doing it until we get a all 1/2 solution.
Wait, but when we throw, we want the solution where there is no nodes that are smaller than.
Yeah.
So we want the solver to output a vector.
Yeah.
0.5, 0.5, 0.5.
Yeah, exactly. And so
why it is better than our 3 previous reduction rules?
Okay, so now I will add one more reduction rule, If we have more than 2k nodes, we say no.
If you have more than 2k,
Yeah, so if solution contains only here, and we have more than 2k nodes, then it means, actually by the previous rule, it's thrown away. Why is it?
because it is more than k, the sum of the vector that
Yeah.
the solver outputs is more than k, 2k times 1
Yeah.
half.
So we are building a kernel function for the vertex cover problem.
Yeah. So we have
Why is it better
k
than
as
our
input.
previous one? It kind of it seems like they reduce to one another.
Before we had k squared kernel,
Uh,
and now we have k
no, so-
squared plus k kernel.
now we have a linear kernel.
Yeah.
Wait, can you repeat? How did we get to the 2k conclusion?
Yeah, we still need to prove that this rule is correct. But now
Mhm.
let us believe this rule is correct. So after we remove these two sets and
Yeah.
correct k, we have equivalent instance. We don't know yet why it's equivalent, but let's believe it's equivalent.
Yes,
That's-
again, the rule is when we throw away all the v less than half and more
Yeah.
than half, and we get more than 2k nodes,
Yeah.
we say no.
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 The rule is that we run it again and again and again until
Yeah.
the algorithm guesses that these sets are empty.
Yeah. And
And-
then if there are more than 2k nodes, we
Yeah.
say no.
Yeah. Because it means that the total sum of solution is more than k, because all the nodes have weight exactly 1/2. So we
Mhm.
have 2k times 1/2.
Mhm.
We have
Okay.
more than 2k nodes, and so number of nodes.
And if the solution for LPVC is more
Yeah.
than k, then we can do it.
Yeah,
Yeah.
exactly. So that means that our optimal value here is more than k,
Mhm.
and we know that then this answer is also false.
Mhm.
And so after doing it repeatedly, we end up with 2k nodes, and then we can do our brute force search more efficiently because the graph is smaller.
And what is the asymptotics of reduction, actually, of this reduction?
So how much time it takes?
It takes to
and-
reduce.
Okay,
You will
so
because
to-
it takes exponential time to reduce it, doesn't make sense.
Yeah, so this runs in time square root n times number of edges m.
Mhm.
To do one iteration. And then in the worst case, you throw away one node in each iteration. So it will take n times n iterations.
Square root of n times m to do
One calculation of the three sets here. So to solve this problem. Solving this problem takes time square root n times m by Hopcroft-Karp algorithm.
Don't know.
That's for linear programming, yes? No?
You just have to run this algorithm, this for bipartite matching algorithm. So you can solve this problem by computing a certain bipartite matching algorithm and a graph whose number of nodes is twice larger. I will explain it in a second.
Mhm.
And then, and this algorithm, one run takes this time,
Mhm.
and from the results of this algorithm, you extract these sets. This
Mhm.
very fast, just scanning the solution. Then the question is, so then we run it again iteratively. How many times do we need to run it?
At most time.
Yeah, at most n, because when we don't remove a node, it means that all the nodes are here. And as
Okay.
long as not all nodes are here, we remove it. So this is the time. Actually, I don't know if it can be improved. Maybe you can prove that in a lot of iterations you can throw away many nodes and then you can maybe improve this factor. I don't know. I didn't try it.
It's actually normal, like nice asymptotics.
But okay, so nowadays there is a better alternative for Hopcroft-Karp algorithm. So you can solve it in time m.
Mhm.
Uh, you need certain precision. No. Yeah, so up to logarithm. But unfortunately, there is a constant here. It's like more than trillion. So in practice, it's theoretical algorithm. And logarithm is to the power 17, something like this. And so
Okay, for
yeah.
some very large graphs.
Yeah.
I mean,
But it's parallelizable. But still, if it's constant, yeah. So it's theoretically, you can.
okay, so it is a polynomial time of the number of nodes and edges reduction, and that's the rate. And then we have a linear kernel, like literally linear kernel. That's good.
I have a stupid question probably about kernelization. So, do we use kernel at each call of the recursion, or only
No,
in the
this
beginning?
is one kernel rule.
Yeah. I mean,
yeah.
we are solving, for example, vertex cover problem with our branching algorithm. Yeah.
Yeah.
So we call we use the kernel at each
Yeah.
call of the recursion of our branching algorithm. Yeah.
Well, in the branching algorithm we discussed from the first lecture,
Yeah.
you need to do this because you want to get rid of all nodes of degree at most 2.
Yeah.
And there exist improved branching algorithms. So we had something like 1.48 or 46, something. Now people can decrease this, like 3.8 or something. And they do it by getting rid of all nodes of degree 3, 4, 5, and
Yeah.
6. Well, they do not, so they get rid of nodes of degree 3. And then they can always pick a node of degree 4 to get advantages. But then for 5 and 6, they have to do something more advanced. So they will inspect the branching tree and see that if they have bad luck there, they can remove a lot of things there, and then they get to this.
Mm-hmm.
But like for 4, it's still pleasant to understand how. But starting from 5, it's painful how their algorithm works. And there are so many cases, and so there's some Chinese people who are very motivated. Okay, so now there is a question: how do you solve this problem? And since it uses bipartite matching, I will explain it because I think it's good if you know about this. So let's. No, I first need to prove the reduction rule is correct. Yeah. So this is a consequence of a it's called Nemhausen-Trotter theorem, and it's from the 60s. So people were already using this technique to solve a vertex cover problem. Okay, so the theorem says that if there exists a vertex cover of size at most k, then this vertex cover contains this set. Then there also exists, let me say it again. So if there exists a vertex cover of size k, then there also exists a vertex cover of size k that contains this set and does not contain any element from this set. So if exists S star the subset of vertices, if there exists, I don't need to say it, if there exists vertex cover S star, then there exists vertex cover S width of size s at most s star, and you have v 1/2 is a subset of s, is a subset of v 1/2 union v 1/2. So it's pretty clear. So here I say it again. If there exists a vertex cover S star, then there exists a vertex cover S that's not larger, and S contains the heavy nodes and is a subset of, but contains not nodes from V smaller than 1/2. So this is all V, such that xv equals 1/2. And here is the same, smaller than 1/2. And here, bigger than 1/2. Okay, so now we need to prove this theorem. So let us write the three sets. So all the vertices are here, and now I need to be careful to draw them in the right order to get a nice picture. So here are all the vertices, and every vertex belongs to one of these three sets. So let us have v 1/2 here, v bigger than 1/2 in the bottom, and v smaller than 1/2 in the top. Okay. And so S star can contain elements from these three sets. So let us make a set here, S star. And now we need to find an S that only contains, so here is equal to 1/2. We need to find an S that only contains elements from here. And so how we will find S? In the easiest possible way. We will add all these elements and remove these elements. So I don't have another color. So our S will contain precisely these elements. So that will be S. So this will be the S that satisfies condition of the theorem. Now we need to prove that the number of nodes we took is smaller than the number of nodes we throw away. So these we throw away, and these we add. So in the picture, my picture is not nice because this area is much bigger, but you get it. So we throw away this from S star, we take these nodes. And now we will prove that this set size is at most the size of this set using optimality of the solution. I mean, that's the only thing we have here. Okay, so let us first think, where can there be edges? Can there be an edge sorry, sorry, I need to change the picture because I made the wrong, like v 1/2 should be in the bottom and v 1/2 is here, so I will redraw the picture. This is S star, and so we will get rid of these nodes and we will add this will be S. Okay, and so now I need to prove that this set is size at least this set here, this here. Okay, where can we have edges from this set to this set. Is it possible that a node goes from here to here?
Yes.
So
No.
no, because
it's prohibited.
sounds-
We need the sum to be
Yeah,
more.
yeah. So that's why I had to redraw. I did it in the wrong. Okay. Can we have edges from here to here? Okay, let's say from here to here.
Yeah, of course.
We can have,
and
and from here to here we also can have. Can we have an edge like this?
Yeah.
Okay, somebody says yes, somebody says no.
Of course, no.
Of course no, why?
Because this is S star.
Yeah. So a star
Ah.
needs to have a node for every edge. So this cannot happen.
The star is what was thinking.
A star is vertex
Vertex
cover.
It's a vertex cover.
Yeah. So all edges have at least one endpoint in a star.
Okay.
Yeah. Okay. So now recall the goal. This is larger than this. What we removed is larger than this. Okay. So we take our solution here, and the plan is to increase the weight a little bit on the edges that are here, and to decrease a little bit. So we want this to be large. Sorry, we will decrease the weights a little bit on these edges and increase the weights a little bit on these edges. That's our plan. So we take a tiny epsilon, and then so we decrease on this set and we increase on this set. And if X is still a solution, then we are done. Because if this has more nodes than this, then in our sum, the sum decreased. So if you have strictly more nodes in this part than here, oh sorry, ow. Okay. We want that this part is small and this part is large. So we will increase in the part that we want to be small, and decrease in the part that we want to be okay, so we want some part to be large. So this part we want to be large.
For each node.
Yeah, so we will decrease in the part we want to be large and increase here. I will write it. Which oh my god, I'm completely senile. So we increase here and we decrease here.
So for
No. We want this part to be large. So we will increase here. Decrease. I'm really sorry.
Why do you want this part to be large?
Because that's the ones we throw away. We want to throw away many nodes. So there is a requirement that our new set S must be small. So we want to throw away many nodes. Oh fuck, I'm again wrong. Okay, now
Maybe you can just say you want the
decrease.
less?
Let's toss a coin. Come on.
No, we want this to be large.
Maybe just like large and small.
No, it actually makes sense. If we large means what? It contains a lot of nodes. If we for each node we decrease its weight by tiny epsilon, and for the part that we added, it also contains some nodes. And we for each node that we added, we increase its weight for some tiny epsilon. And if we get the total sum less than what we have previously, it means that we threw away more nodes than we added, and that's what we're aiming for. That's the
Yeah,
goal.
so it's proved by contradiction. So we want, that's, I forgot about contradiction. So imagine that this is small. And now we will create a problem with this minimality of the sum. So we will decrease the sum. So imagine that this is small. So we will increase their weight, and this sum, it will create only a small increase, but we will decrease these weights. And so then if this is indeed smaller, then we can decrease the sum. But we said that we compute an optimal value of the sum, so it's not possible. So that's our plan. But the question is, when we do this change, these nodes get smaller weight, these get larger weight, these get smaller weight. If we do this, we need to verify that all constraints are still okay. That's the only thing that remains to be done. Okay, so now let us think where can be the edges. So which ones do we need to, so the plan is to decrease epsilon, so that all after this decrease, all nodes that are here are still here. Okay, that's why epsilon has to be small, but otherwise we don't care. Yeah.
We always can, because we are in discrete world.
Yeah.
Of,
Okay, so we need to pay attention to the nodes that for which one of the endpoints had a decrease. So nodes with endpoints here, we need to check that everything is okay. And so where can they go? They can go to here. There are three possibilities. If they go here, then it's still okay, because after the decrease we said at least 1/2. If the node go here, we are still okay, because for the same reason. We are in the heavy nodes. And if they go here, the edge, we are also okay, because here we decrease epsilon and here we increase epsilon. So this condition is also okay. And as we already said, we cannot go here or here, or inside here. So that's proof of Nemhausen-Trotter. Sorry for my explanations. It's very logical, but then you have to flip many times because of contradiction. Yeah, no excuses. I should have trained this.
but so we have proven that if we.
But by the way, I looked to other teachers on YouTube. They're also wrong. I thought, oh, it's logical. I will not make this mistake. But yeah, of course. Yes.
That's amazing.
So now we understand. We add these nodes to the vertex cover, get rid of these nodes, and then we know that if there is a good vertex cover, we still have one. So the answers are equivalent, and we repeat. And
we have proven the correctness of our reduction.
Our reduction rule. Yeah. Okay. Now the next question: how do we compute the solution? And then there is a pretty amazing trick. So I will explain how it works.
How do we compute the linear programming
Yeah.
solution of the task?
So this we also don't need.
That's really true.
So there is a theorem that says that there will always exist a solution where the values of x are 0, 1/2, or 1. And moreover, we can compute it fast in time and to the time I wrote down. So there exists an algorithm that outputs optimal x in time square root n times m. Moreover, this optimal x belongs to 0, 1/2, 1 to the power n, and is number of nodes. So that's our next theorem.
It basically says like we know that we do not take this to the vertex cover. We know that we definitely take
Yeah.
this to the vertex cover, and we kind of don't know
Yeah.
whether to take it or not.
Yeah, I mean, it's not obvious that there exists such a solution.
Of
It's like
course.
two theorems inside each other. There exists half integer solution, and we can compute it efficiently.
Mhm.
And so algorithm is as follows. So you take a graph and you create a second copy. I will just take a triangle because it's a lot of work. So we take a second copy. Well, except that we don't, so original will be the triangle. And instead of drawing the edges, for every edge, we create two edges in the copy. So here is an edge. We connect the nodes in opposite graphs.
So we create.
So this goes here, so it will go here, and this will go here. So we create a cross for every edge. And then we do the same. So let's look at this edge. So it is this edge. Okay, maybe so let's look at this edge. We create a cross here. So it goes here, and it goes here. And then the third edge. No. Like here and here. So this is a graph, and it's bipartite graph. Do you remember what's bipartite graph? So all the edges go from one side to another side.
Mhm.
And now we compute vertex cover, or we compute maximal matching in this graph. Sorry, vertex cover. I mean, it's the same problem actually in bipartite graphs.
What
So-
is maximum matching?
Yes, and this trick is really good for finding maximal matching
Yeah,
also.
yeah. So, but we will use vertex cover and bipartite graph. It can be easily solved by this Hopcroft-Karp algorithm. Or there is some Russian guy who published the same time. I forgot his name.
Edmund Scott.
Yeah, but Edmonds, in 1973 there were two papers here in Russia and in the US, I assume. So it has three names, but I forgot the third name. So I'm bad citizen now. Yeah. Okay. Yes. And then we want to know the values here.
Can you write down the two names?
Hopcroft-Karp.
Yeah.
Yeah. So Hopcroft. I don't know, maybe two piece. Karp. And then the third one, I forgot. But in this book I gave, they didn't say the third name. So the
Karzanov.
Karzan, exactly, Karzanov.
Alexander Karzanov.
Yeah. Okay, and now when you have the solution here, so for every node there are two possibilities, either it's in the vertex cover or not. And here we will take the sum, the average of the two values. So we say if it's in, we call it 1, otherwise it's 0, and here this node we take the average. So for this node, like we are interested in this node, we look here, if it's 0 and 1, we give this node 1/2. And if in this node it's 1 and 1, then we will call this node a 1 node, and so on. So that's how we get the solution, the half integer solution. And now we have to prove two things. So we have to prove that for each edge, the condition is satisfied. So that we have to prove that our solution is indeed a partial vertex cover. And secondly, that any other solution is worse. So any other partial vertex cover has smaller sum. And so we can understand the first task is easier. Why for every edge do we have at least sum of these two values equal to 1? So,
Because otherwise it's not LPVC.
so for every edge, remember we have a cross here. And every cross has at least one endpoint in the vertex cover. So if we sum up the 4 values, we have at least 2. So if we take the average, we have at least 1. So we get solution. And remember, every edge here becomes a cross on 4 nodes. And this is a vertex cover, so we have edge. Okay, and now the question, why if I take another set, the solution is better? Oh, and this I forgot. It has to do with matching, like the duality, but do you, some clever guy, remember how this duality works? It's very basic thing, but I cannot remember it now.
What are we trying to prove?
We want to prove that if here we take any other solution, then the value is at least the sum of all x's is at least the sum of all x's here. And so for this we need to recognize a matching here. We want to find a matching and the number of nodes is at the number of edges in the matching is oh, I'm really sorry, I forgot the last part of the proof, but it's in the book if you want to know about this. Yeah, okay, I should have. To be honest, I expected 0 students. Okay, but
Yeah.
so what's the time, by the way?
The time is 7:28.
28.
So we are like finished with this pair, and we can have break now.
Yeah. And let's the 3 with let's skip all the other things.
Will we
Because
discuss the 3 colorability problem?
Well, I can quickly say how. Okay, I can explain. It's
Yeah.
like 20 minutes or something, and the 3 with decomposition. I think it will be important technique in the future. So I will explain it to you, but you won't need it in the next 5 years. But maybe
How do you know?
because I worked for a company and I see how they progress in the book extremely slowly. So they yeah. So can you pause this?
Alright guys, you don't need to see this.